So we realized what we didn't do at the beginning was to give a little bit of context of what Burrow is and what it's trying to do and where it fits into the landscape of Hyperledger tools. So it's a little bit late, but let me give a little bit of context here. So Burrow is the oldest, as far as we know, it's the oldest permissioned blockchain that is open source. It's at this point a 4-year-old code base. When we started building the code base that is now Burrow, the basic ideas of doing a permissioned blockchain were thought of as heresy, but we thought it was an interesting idea that could solve some real-world business problems. And so initially what we had done, because we were very focused on process use cases. I'm a lawyer by training and a technologist by habit, and so when we started, I was very interested in thinking through a lot of process use cases that I saw as being, as blockchain being a real enabler for it. And so we took a very early version of Geth. This was before Ethereum had even done their ICO. I don't think they had testnets at the time. And we pulled it apart into two components. An application engine, as we called it, and a consensus engine, as we called it. And in between those two, we inserted a permission layer, or an access control layer. Not really an access control layer, more of a permission layer. And that seemed interesting to the market. We closed a funding round for my startup, and then we started working on the code base that is Burrow. Over the last 4 years, we've probably done, I don't know, 5 complete rewrites of the code base, more or less, or very significant refactorings of the code base. The most recent was Q1, Q2 this year, where we paid down a bunch of technical debt that we've been acquiring and put Burrow in quite a good state. So what is Burrow? Burrow is essentially an Ethereum virtual machine on top of a Tendermint consensus engine with a permission layer in between. And that permission layer is operated by a system of Go-based contracts that we call secure natives. And within Burrow, you have an ability to add some new functionality in native languages, although that requires you to recompile the binaries because Go doesn't really have an elegant plugin system. Does technically, but it's a nightmare to work with. And then we have evolved the tool in a manner that where we think it fits into the landscape is as a fast, lightweight, easy to use blockchain framework that gives you an ability to really focus on process heavy use cases, which is why we currently use an EVM. During the next year, we will be prototyping and then moving into the main line of Burrow using a WASM interpreter as some of the more Ethereum-based tooling moves in the direction of leveraging WASM. It's a single binary that we statically compile and has pretty much all of the tools that you would need embedded in that binary. So what we have shown over the course of the workshop so far is how Burrow has inbuilt all the tooling that it needs to set up blockchain networks, to run those blockchain networks, and then to deploy contracts or systems of contracts onto those networks. And those networks can, as we like to think of them, those networks can evolve over time, which is sort of the second piece after we spun up the network that we're going to show you now. And so over how we fit into the landscape of other Hyperledger tools is that we have fewer features, and that is by design. We have fewer knobs to turn, we have fewer bells and whistles, but we can be installed with one binary and get up to speed relatively quickly. And so we're a lighter weight framework. We're less modular than Sawtooth or Fabric is. We don't have pluggable consensus. We have an opinion about consensus, and that is that blockchains are about Byzantine fault tolerance, and we have been longtime users of the Tendermint project, which is, in our opinion, the most mature, provably Byzantine fault tolerant consensus engine that exists within open source. Which is not to say that other people's opinions are wrong, that's just an opinion that we take. Burrow is built to be fundamentally a permissioned blockchain. It can be put in more public settings with a network that we are co-founding with another 15 or so companies currently. That's called the permission layer, that's called the Agreements Network. And the Agreements Network runs on Burrow, and when the mainnet goes live later next year, we will have a public permission network. The only permissioning capabilities that we will leverage from Burrow, essentially what we will do is we will turn off all of the network administrator privileges that exist within Burrow. Those will be turned off. All of the other permissions will be turned on, so that anyone joining the chain can do most of the things that you would do with a public blockchain. There will be a governance mechanism, however, around new pieces of solidity that get added to the chain. So anyone will have an ability to propose to the network that new code gets added to the chain, and the validators will then vote on them. So we have a mechanism that exists within Burrow called the proposal mechanism, which I talked about earlier, that allows you to essentially set a voting protocol for new things to happen within the context of the chain. And this is configurable. You can leverage a proposal mechanism to do high-level governance stuff for the network or other things. So that is a little bit about Burrow. Happy along the way if you have questions, but I realize, thank you, Swida, that we didn't give a little bit of context at the beginning. We probably should have done it, so my apologies.
We'll do it tomorrow. Yeah. And just a couple of small additions to what Casey was saying. So, and one thing,
I'm the CEO of Monax. We're behind Burrow. Silas is the CTO of Monax. He mostly develops Burrow. So all the problems you have, blame him.
Yeah, should have said that as well. So yeah, we have fewer features in terms of pluggability. One very important feature is the BFT consensus, and obviously the EVM. So there are not a direct subset of other projects right now. One thing to say about the permissionless public thing. So one design pattern that we are using for the Agreements Network is ultimately no human being will be able to call or deploy contracts. Everything will act through a proxy contract. And that combined with the proposal mechanism allows you to have an orderly transfer succession of kind of axiomatic contracts for your network. So we're implementing an Agreements Network on top of Solidity, but we're not providing a blank slate Solidity network. So the permissions kind of interestingly allow you to do a public network in a way you couldn't exactly do on Ethereum, whereby you only let the computers update contract and do stuff that you'd be able to do on Ethereum. Anyway, so is everyone up to where we got to with connected to the chain? Hey. Yes. So we've been having, there's an issue now with restarting. So if you, where's Sean? Could you just show them how to get it back up? If you delete Burrow data directly, it'll be a quicker cache. You can delete the whole Burrow data, or you can delete .burrow/Burrow save.db.
I was wondering about the scalability of the consensus you guys are using. Would you say that as the network grows in size, like thousands of nodes, maybe that's not the best, or then it might make sense to sort of something like that? So as long as you have a relatively small, in the hundreds of nodes, then it's a very good choice. But as you grow, then that might not be the best consensus. Or
so disagree. Both, we agree and disagree.
Yeah, we agree and disagree. So I think it's important to separate the notion of a node on the network with a validator on the network. And the way that Tendermint consensus works at a at a sort of 30,000 foot view level is that one of the validators, and it's a round robin with a little bit of randomness, one of the validators says, this is what I think the block should be. A message goes over the gossip network to all of the validators. They do what's called a pre-commit, essentially saying, yes, I think that should be the block. Those messages come back to the center of the network, and then another stream of messages is gossiped out that formally votes on this transaction getting added to the chain, and then those messages come back. So you have a gossiping sequence that has to start with at the center of the network, go to the edges of the network, come back to the center of the network, go back to the edges of the network, and then come back. And this is how the BFT protocol that Tournament has outlined works. And so you can't really, I mean, you certainly cannot get to an infinite number of nodes on a network like this because you never get to the edges of the network, right? And so in theory, so Tendermint has tested networks up to 500 nodes, and those networks have started to get very, very slow. Just because of network latency and all the messages that you have to do. And so if you are in a situation where you need to have thousands of validators, Tendermint consensus is not going to be the best one for you. In general, no proof-of-stake system is going to be good for you because proof-of-stake systems are essentially weighted voting mechanisms, and you're going to have something like this message passing sequencing that's going to happen on any of the proof-of-stake designs. And so those systems are not very well able to handle thousands and thousands and thousands of nodes.
Which is fine unless you have a very good reason to have thousands. So
it's thousands of validators, I should say. You can have thousands of nodes. You can have thousands of nodes, but if you need thousands of validators, then you have a really interesting use case. If you need thousands of validators.
That was my thing. I just was.
Yeah.
Maybe just understand to the network you guys are bringing on top, so the authorization. Is that the name? Authorization network?
Agreements network.
Agreements network. So here, you don't necessarily have a need, especially as you're focusing on the application. You don't have a need to onboard, say, 200 validators. I mean, you could work.
We want to get to about 50 when the mainnet launches.
Yeah.
And then we're happy for it to evolve up to 500 even over time.
Yeah, okay, just want to check, because for small networks where you need to have some decentralization, but 50 is good enough, then that's perfect.
Yeah, exactly.
But we have spoken about scaling in terms of joining networks together, and that's how you scale PBFT style algorithms, right? Which have their own advantages. Yeah, exactly. So, and they reckon that they think the right size for an individual hub or zone is probably going to be between like 200 to 400 once they get it to there. You get to a theoretical limit of just around the message complexity, basically on all PBFT variants. But that's not to say that they can't scale well in that way.
And that's where the meta protocols that can interconnect individual blockchains can start to become really
That's how you
important.
should scale. I mean, there's no all the data ever great goes.
Well, it's how the internet fundamentally scales. I mean, I always push back on the idea that a public blockchain is like the internet because I find that analogy really not
I have all
true.
the websites on the world on my laptop.
Yeah, exactly.
You know.
I mean, the way that the internet works in practicality is just a routing layer on top of a bunch of extranets, right? I mean, you go to Facebook.com, okay, you're going to Facebook.com. How many computers do they have underneath Facebook.com, Google.com, et cetera? I mean, those are just a series, it's just the tip of an iceberg of extranets, right? And so that's why, for me at least, meta blockchain protocols are really what the interesting thing is going to be going forward. So.
Okay, so I don't know where people are. I know there's some issues going on, some of which are a little surprising to me, but most of them been able to catch up if you may have needed to delete your Burrow folder. Something you can do against your local node is hit the status. So, and that will tell you whether you're catching up over here, and you'll be able to see the latest block. So we're running at block 8,893. If you have a crash at catching up at 5512, I'd be interested to see that. I had a crash there as well, so something screwy has happened in this process. But let's try and power on and see if we can get up to the next step of this. So bring you back to here. So I think everyone had done a contract deploy of the get set who was following along. So what we did there, we were connected into the main network. Now our nodes have synced up, but we're not validators on the network right now. Is it happened again? Interesting. Okay. I'm surprised that it happened for me that once, and then I got past it. Surprising.
For a blockchain, it is surprising.
Yes. Yeah. Yeah.
Deterministic. How dare it?
Exactly. Yeah. We'll have to come back and have a look at that. But the next step that we wanted to get onto though was making people an actual validator. So here, what we're doing is we've got an all-powerful key at the moment. This Uber key beginning with BE60. And that's actually deployed and it's available to all of the validators that are running in our cloud. And they're acting as delegates, so that when you're able to talk to those nodes, they're signing with this key. What we're going to do, you have this key locally actually, and it's acting as a delegate. What we're going to do is we're going to add each of you as a validator with a little bit of voting power. So if you have a look at the add validator YAML, which is in that 03join-join folder, which I could bring up. So this is using a method from our governance. Now, Casey was talking about the proposal mechanism. Ordinarily, no account. Well, I say ordinarily. You can set this up how you like. You can have a super user if you want. But the way that we'd use it in a real network would be that no human user would have this power, this root permission to arbitrarily update accounts. What we'd do is we'd give it to a distinguished system user that no one could control, and then we would run stuff like this through the proposal mechanism. But here what we're doing is this key that you have access to has this root permission. And what we're going to do is we're going to run a jobs file that gives you two things. First, it's going to give you a little bit of native token. So this means that we can actually use it to send transactions. There is an implicit relationship between holding some token at an account and that account being created. We're also going to give this account a little bit of voting power. It's got an order of magnitude less than what the validators have in the cloud, just to help keep the network rolling. We need to have 2/3 of the total validator power available at block voting time in order for the consensus to move on, right? So if we drop below, we need strictly more than 2/3. So if we drop below that, Tendermint will halt. So that does the update and will make you a validator. These last two just do some checks by querying the validator set, and then there's some back reference stuff going on here. So it's querying the validator set .your address .power. That pulls it in, and in the job syntax assigns it to this check power job, which itself can be back referenced. And then we've got this rather verbose equality check embedded in this YAML language here. If all of that runs, then you'll see a success message. So let me put you back on to the bit. So you should give that a go. So you need to have your key that you're running your validator with. So when you did your Burrow start -A, you need that key.
Does everyone have access to this so they don't have to type it in?
To the slides?
Yeah.
No.
Okay.
We can just type in.
If you go to the Burrow rocket chat room, you can see the slides, and so then you can just
Yeah,
if case of modify that command, because that's a pretty long one
Sean,
to type in.
Greg, could you chuck the
He did.
slides to the...
Dave did. Or Dan did, sorry.
They're probably scrolled back a bit, aren't they?
No,
Okay, cool. Let's just have a look at what's going on over here. Again, so can you show me your local directory? Can you show me what is? Yeah.
This is the hash, global hash.
Yeah.
Did it work?
So let's have a look at what you've got with the
in management.
Oh, okay. You're just here to listen, okay.
To see what is possible.
Nice, good.
Okay, let's check one.
Did it fail for anybody? It worked. Great.
You're getting deterministic, non-deterministic. Yeah, so let's have a look at in the change there.
It worked?
Yeah.
Great.
No, but I want to ask you something.
Sure.
Show me where you're
When I look at the validation, you know, they would want to have the same power.
Where's these?
Yeah, so the power essentially equates to awaiting voting messages. And so the way that the consensus engine works is your node will have a certain percentage of the overall power. So the nodes add up the total power that has been that is available in the system, and then it divide your power divided by that, and that's how many essentially votes you get within the protocol. And so it needs to be greater than 2/3 of the power to vote on a new block. Greater than 2/3 of the total power needs to do that. So I think we just made that number for the purpose of this, to be honest. So and I think they're relatively significantly weighted, so that if you guys go offline, the network will still run. So actually, no, it's not that weighted. So anyway.
No, I mean, the fact that I saw this, although it's very odd to me that I haven't repeated this again.
Did it work for you, Vlad?
Almost.
Almost.
Basically, every time I stop the boat line
Are you hitting the same app?
as well.
Are you hitting the same app?
Yeah, I mean, what happens is that
You catch up to 5512 and then you it does?
I think so. Actually.
Yeah.
Yeah,
it's
I'm
a-
not sure that, so.
Well, that's good. That's a new.
That's a new vibe.
Crazy thing is that when
You love your kids.
Just one question for the station for it. So, I mean, I guess your idea was over time to start adding external partners. Because I guess yeah, well, that's what I'm asking. No, well, essentially the thing I'm curious about is there any notion of token like
So we do have
as a smart contract or built in
It's built in. It's built in,
but
and
it doesn't have to be something you can build on top of.
it's built into Burrow, not Tenor.
Okay.
There's tokens in there by default. And we will be adding, we're currently adding governance privileges that we can leverage at higher levels to do networking stuff. We'll be adding token economic primitives that you can configure when you do this.
Okay, because we had to implement a bunch of our own token economy stuff on top of Ethereum. Another question related to, I mean, that's cool. It's cool. That means, okay, we can totally, technically take all the code we've imported, swap out Ethereum, and most of the logic, everything is in smart contracts and stuff like that. So it would be very easy to swap whatever the changes are in. So two questions to that. First, addresses and signature and all of that. How Ethereum compatible is it? Not just the solidity, but like address and so on. Because we are using a lot of those primitives from Ethereum. So if we were to play around it,
Just have a look at the app hash error you've got. Can you have that handy in time?
which one?
The app hash error where it failed.
This one.
Yeah.
Well, if I start,
Oh, you caught up now?
yeah, no, I had to restart. So I
And you
deleted
caught
my
up?
border.
Okay.
It's like
Maybe if I stop and I restart,
yeah. So what's happening here? I've seen this. Something in this check. So
someone's trying to mess up with.
Yeah, we're getting DDoS.
right.
This workshop is high value.
What I'm going to have a look at is I'm going to run some forensic stuff to see if I can.
I can back this to a VM and send it to you so you can say it's on the VM.
Let's say we're going to start playing around and see how that works. Because most of the value.
I tried like 5 times.
Yeah.
We're going to do the transaction first. Interesting. So if we
That's
we have to start changing the way we generate addresses and all the proofs and all that stuff we're doing because we're using the granularity of that. That's the first question. And second,
Should. I mean, obviously the addresses themselves will be different.
sure, of course.
But as far as I know, there's no differences. Other than that, well, so there's 2 differences. Obviously, you would have different, maybe if you change, you would have different, you would have different. The other piece of it would be, this would depend somewhat on how you determine it. The validators and the signing is based on UDP 509 keys rather than SSH keys. And so, depending on what you need to prove, there are some primitives that are exposed in, I mean, the shop primitives and all of that stuff is exposed just like you did in
That's the thing I have, especially if you, I mean, because like if you got other chains that like different spaces they're using, so if I've got compatibility, then
it's basically the same thing, yeah. I mean, address spaces and all that works is basically exactly the same.
and then I mean another.
I mean, we store it differently, depending if you use a level DD level, but, from the smart contract perspective, it's not this, right?
Yeah.
I mean, we use Tendermint's IAV L3 rather than the traditional 3 Ethereum, but that should be a lot different.
I think it's stuff worth saying around, and I mean, now more philosophical question. Imagine you have a chain, we run our mainnet for a while, and I want to argue for various reasons. Let's say technology works a lot better, we're a lot happier. And obviously, for the history of a chain to another, it's going to be more blocks. If you don't have that, so you would have to, you would lose the history of everything up to there. And that's obviously not viable, but I guess. Or you just
So it really depends on the use case. So yeah, it depends on the use case. So for us, the important bit is not necessarily the block level history. It's the state. It's the current state of the change.
Sure.
And
You can take the whole history and put that as a starting.
We have a dump restore system, which essentially allows you to dump the state and restore it into a new block, and then you can have validators essentially approve one or the other. You can then archive those blocks, so you don't have to be there.
That's another option.
So you can still have the proofs on the old validator.
So has anyone successfully managed to add themselves as a validator yet?
Yeah.
Been able to run that job and it complete? Okay, cool. So let's have a little look, because I'll try and keep this going while I work on this curious issue we seem to have come across. Okay, so first of all, before we do that, let me see if I can find some of you guys as validators. So I deliberately gave a curious validator pair to you. So we can hit the validator's endpoint, and if we go into less, if I look for 9991, okay, there's a few. So spot yourself. Who is D2AB6 and who is 664 C? Or well, I tell you what.
89CB is the last one.
Uh-huh. That's you?
Yes.
Okay, cool, yes. I was like, yeah.
Yes, you validated me.
Yeah. So what you should see, now at this point I'd get you to close your burrows, but now I've got a fear about that.
So we have 4 of you that have joined the network,
Yeah.
looks like.
Yeah, it looks like that. You will occasionally, with that much validator power, so you get a chance to propose blocks roughly in proportion to your validator power. It's determined...
Oh, sorry, I was just,
Oh.
you caught my attention to something else, but keep going.
It's deterministic how the proposer cycles around based on a kind of accumulator. So it's a sort of mixture of how much of the total validator power you have combined with how long ago it was. The longer it was, the more likely it gets. Eventually it will be your turn. Yeah, what was the thing?
No, sorry, I was thinking about something else, and then you said a word that kind of made me click in a different way, and I was like, oh wait, so that wasn't a question. It was just kind of like, wait a second.
Okay, so cool. Let's get this JS app going. So for this bit, we provided you with some JS code.
So high level, what's about to happen? Just to review. So we started a network on our laptop. We just to show how developers typically run things. We tore that network down. Then we generated a key and joined a communal network. And then we all made a Burrow deploy YAML and deployed a contract to that chain. So everybody that participated in that has a chain, has their contract that is running on that chain. That this chain will have multiple versions of that contract. And now what we'd like to show is typically the typical way in which people interact with Solidity-based smart contracts is via Node.js, a Node.js system. And so now we're going to show a little Node app and that will be running, and we'll interact with it to again change and interact with the get set contract that we have deployed onto the chain. But in order to do that, we need to move a couple of files around. For anyone that has not worked with Ethereum-based systems, management of what are called the ABIs will become a bane of your existence. They are an absolute nightmare for whatever reason to manage. We will have a feature at Burrow that will allow you to store these on the chain going. Probably in Q1 we'll ship that feature because it'll make things a whole lot easier. So what you need to do is to do those two copy commands. And that's going to copy, well, cd into the 06 directory and then run those two copy commands. And those commands are going to copy, first it's going to copy what are called the ABIs, and then it's going to copy a JSON file that's called an output.json file. The ABIs are a way in which to serialize and package transactions that need to go to a contract. ABI stands for Application Binary Interface, and it's the primary way in which you interact with Solidity-based smart contracts. It allows us to say, if you remember when I showed the deploy YAML earlier, we said, here's the destination of this transaction, meaning here's the contract that I want to interact with, here's the name of the function that I want to interact with, and here's the parameters that I want to send to that. Underneath the hood, Burrow deploy then takes that and packages it and serializes it in via these things called ABIs. And that's what allows the Burrow deploy system to interact with a particular function within the compiled Solidity that exists on the chain. At the end of Burrow deploy, what we do is we create an output file. And so the output.json, it should be deploy.output.json. That is going to include the address of the contract that you deploy to the chain. Okay, and we're going to use that in the application here to understand where my address, the address of the contract that I deployed, is within the context of the blockchain environment. Okay, so once you do those, then run npm install, and that's going to install just a few packages. This is a very simple Express server. It's going to, I think there's just Express and Burrow.js. For anyone that may be familiar with, more familiar with the Web3 community and the general Ethereum tooling around that, Burrow.js is a rough equivalent to Web3. Burrow leverages primarily a gRPC interface. Burrow.js is a gRPC-based system that's talking to our gRPC, the major port that we leverage. Once we get through npm install, let me know. when people have gotten to the end of npm install.
I've tried the next one.
Sorry?
I tried to start with the test and so,
Try it and
yeah,
test.
this works.
Oh, test works.
Yeah.
Oh, okay.
Exactly.
That's my fault because I hardly ever work with Node. So don't go to npm test instead of npm start quite yet. And if you have, just Control C to cancel it. If you have not changed lines 19 and 28, can you show the file?
Which file?
The app.js.
Sure. So I have somewhere, which I can't see my bar on this side. Let me transfer it over. So,
Do you have line numbers?
uh,
Okay. So anyway, the first line is to change. The first line you'll need to change is line 19, and there you'll want to put your account address.
so this is your My Lovely Key address, right?
Yeah. So that's the address that you've been using all along. There, and then scroll down to line 29 or 28. No, 28, not 30. The deploy simple storage. That needs to be
Yeah, so
the
that's-
same as the output of your job.
So you'll find that where you've run the deploy of the contract, you'll have a binary folder, and you'll have an output folder. So this gives some metadata, including the deployed contract address. You don't know the address that a contract will get deployed to until you deploy it. It's a deterministic sequence based on the input address deploying it. But if you fix those up so that they point to where those files are, so if you can find the deploy output JSON and the binary, which has the ABI in it. So if you're having any difficulties finding them, I can come and help you out.
So it should be, line 8 should be bin/get-set.bin. They copied in the deploy YAML and
Okay.
And then once you change those files or change those lines of this file, save this file, and then you can run npm test. And if it doesn't throw any errors, then we're good to go. Anybody have any questions or everything okay?
So we make the changes and then
Save the file.
save the file
And, and then npm test.
and npm test.
Yes. I'll maybe go back to the presentation.
Yeah.
Q.
I
And,
have a question.
yep.
So this thing that we have.
Yeah, yeah.
04,
No, because we copied that in. We didn't copy.
It's even on the,
Oh, it called it simple stories. Okay, just copy whatever that is. That's fine.
it's actually way in front of time in hash matches.
Okay. Great. And then. Great.
Because hash, it gets, it matches this hash.
While people are getting started setting up or are finishing up this bit, this sort of begs the question of kind And within enterprise grade systems, typically we see a pattern that that takes a node, typically node, doesn't have to explicitly be node, but typically takes node as and takes and operates a node application as a RESTful component that sits between what the blockchain needs to see and what other business systems need to see. And so, you can use some JS, obviously, in front side, on the front end, and have a browser talk to a blockchain directly. We find that is typically not a very efficient pattern. Obviously, it depends on your use case and what you're trying to achieve at the end of the day, but that pattern has some real challenges. One of the primary challenges around that is that currently gRPC doesn't work in the browser, although Google is working on it, at least for Chrome. It doesn't really work browser side currently, unless you're very, very bleeding edge. And so that presents a challenge for those blockchain clients that leverage gRPC significantly, which we do, to be able to interact with the blockchain at all. You have some challenges there. So the typical pattern that we see is this idea of you have a blockchain cluster underneath, you'll have one or more node applications on top of that, and then you'll have your other business systems or browsers that will talk typically RESTfully to a node, to one or more node applications, and they'll be the ones that will typically do the translation into what the contracts need. And this pattern with Ethereum-based systems, this pattern means you really only have to manage and wrangle these ABIs files in one layer of the stack rather than multiple layers of the stack. And it allows you to add additional business logic or checks that you might need in the node layer that you don't necessarily want or can put in the blockchain layer itself, and so that's how we see that's a very typical pattern that we see time and time again across a range of frameworks. So that's why we're showing this portion of the node application. So we have a get set contract that's on the chain, and now we have a node application running. So now we're going to use curl. Can you go to the next slide, please?
Yep.
Now we're going to use curl to talk to our node server, and that is going to talk to the blockchain, and the blockchain is to the contract that we deployed onto the blockchain, and it's going to take it from there, unless we didn't screw anything up. So we're going to save a little URL variable to make it easier on ourselves. That should be by default HTTP, basically localhost 3000. If you didn't change the node application port that it's running on, then that will be the URL. And then you can curl the URL, and it should return to you in the command line what the value currently stored in the contract actually is. And that should be the value that you set within the deploy YAML that we did earlier.
This is a lot you push up. Okay, so the social no, you're not catching that. This looks like six.
And then you can see the post there. The second curl command is the post to do a different value. And that will go to the set command, or the set function within the contract that we deployed, rather than the get function. You can change that number, can be whatever you want. As long as it's an unsigned integer, it could be 2 million, it could be 200, it could be 2, it could be 17 million, whatever you want it to be. And then if you run the initial curl, you should see that, that it's the same again. Sorry?
You were saying something about import 3,000.
Mm-hmm.
This command is not working for me.
Okay.
It says,
Oh, sorry. So, curl 3000 is the node application running? Okay, good. So let's see. Address. No, yeah, that's fine. Yeah, no, that's all fine. So we need to go to app.js line 51. Okay. Scroll up. Okay. Can you open your deploy YAML? Or the output, sorry, the output file, which should be in the same folder as this. Yeah. Okay, so deploy storage K. That was the address of the chain the initial. So copy that, deploy some storage K. Yeah, copy that. And then go to your app.js and
It's
line 28.
So Vim,
Right here. So simple storage. Replace that. Oh. Yes. Just deploy storage K. It should be deploy dot deploy storage K.
I can also correct that file, but that's fine. If you read
With capitals. Yeah. And then you do that one. Okay. Now, Control C out of that, and we restart it. Okay, now, right. Yep. Okay, great.
so what were we changed here?
So what we changed was the name of the job.
To look up in
Right.
in this JSON.
Exactly. Anybody else having any problems talking to the app? You good? Great.
I got a question.
Sure.
So, validate-
Now's the time for questions because we don't have any more prepared content. So we're pleased to get this far.
validators are like the peer nodes in
Mhm.
Fabric?
Yeah. So they would be the better ones to answer that, but yes, pretty sure.
So Fabric doesn't have. So Fabric doesn't have a clear correspondence, right? So Fabric's consensus is split, as I understand it, into two sets of entities: endorsers and the ordering service. Consensus validators, to our mind, are the ones that do the ordering. In fact, ordering is consensus.
So can we compare validator to an endorsing peer in the Fabric?
Kind of not. I think so. I think that all that Tendermint sees is opaque transactions. Its job is done when it's put them in a firm order. The endorsement happens on every node effectively via the state machine. So the state machine, the inputs to the state machine are all ordered. Everyone sees that same order. It runs through the state machine and generates a new app hash that contains that. If, as we're seeing over here, there's a disagreement in that hash, then something's gone wrong because each state machine runs the same. So if we were to reject a transaction, which might be, I guess, a bit like not endorsing it, then that would happen because something about the transaction was invalid. So, for example, the signature may be wrong.
Mistake could be.
Yeah. We can have failures in the execution, actually, that technically in Burrow, and this is kind of to do with the way the Tendermint is set up, we could do it different ways, but we have an initial lightweight check that runs on the mempool that will eject transactions that have bad signatures. We don't run any EVM code. So there could be something that blows up the EVM, and that transaction will technically be included, but its state will never have taken effect. So we run all of our updates in this kind of Russian doll state cache thing. So we run it. We run a transaction against a cache of all of its changes. Now we only commit those changes back if it succeeded, and it is possible for it to not succeed. You'll see the transaction in the blockchain, but you'll see it had an exception. You'll be able to see various tracing information for that. So yeah. Yeah, so we don't have different classes of validator. Validator is, I guess, taking part in the ordering, and that ordering is a fully distributed BFT ordering thing, and it's every validator is running the state machine. The other type of node, which is exactly the same binary, no difference in that, is simply a node that hasn't been added like we've done with the governance process there as a validator, and just connects as a peer. By default, anyone can come in and sync up their network a bit like you could with a public blockchain and see those transactions. We have the ability to set authorized peers, so only those can sync. And coming up is the ability to only have peers on the network who introduce themselves appropriately. So link their P2P identity with their validator identity, and at the same time can actually, as they come up, bond themselves on. So that's a kind of a thing that's coming.
So at the beginning, our node wasn't a validator, then we become a validator?
Yes.
And we need that to interact with the network?
You need that in order to participate in the consensus mechanism. When we're sending transactions using Burrow deploy, all that we require for that input account is that it has the appropriate permissions to send a transaction, and that it has received some token to implicitly curate it. We don't need our node to be a validator to use it to send transactions. The node that's a participant can receive the transactions and gossip them, and then it's up to the validators to decide whether they'll accept them or whether they're valid. Your local node will do its own local check against the check.tx signature and will reject transactions for you before even sending it to the network if it fails that. But what it doesn't get to decide is what ultimately gets included. The very final check is after the gossiping of the transactions, a validator, and only a validator, whose turn it is to propose, will reap transactions from the mempool, and then gossip around those block parts. Every other validator will then vote on that block, and it will do so having checked the signatures, then run each transaction in order, decide that it agrees with the app hash in the block that says, if you start with this block, run these transactions, you'll get this hash. If it agrees with that, it will vote them. If it doesn't, it will vote against them. And it's possible for validators to skip around. But a commit only happens when 2/3 of the pre-commits have been collected, and then that's a commit. In a fast network, there's enough time with the block cadence that most validators will vote on every block. Reward models can be built around how available validators are, and punishment models can be built around validators that vote the wrong way. Also.
Which does bring up that I think is that one thing that this brings up is that Burrow does have an inbuilt token. Folks can use it or not use it if they so desire. It can be useful for certain times. For other use cases, it is not particularly useful. As we position Burrow to be more along the public permission lines and to be more useful in that context, we will, over the course of the first couple of quarters of next year, be working on primitives for token economics, which will allow you, when you set up a network, to configure those primitives in a way that you can do various things with algorithmically generating tokens, adding in reward mechanisms for validators, slashing their bonds, or essentially punishing them if they misbehave, and a few other primitives that we'll be building in there in a similar manner to how we have primitives around governance, which we're working on now.
And even when you don't have an extrinsic value you want to attach to the token, If, for example, you have in your Solidity contract that it requires a little bit of value to be transferred, and then you have your accounts that are starting off with some reservoir of value, you can think of it as like almost a scheduling, rate limiting thing on your network. So if you control those flows and how they come back, then the point of the token in that case and the point of the permissions is they're kind of a coarse grain approach to that. You can do fine grain stuff in the Solidity level, but you can set certain like upper lower bounds by, yeah, okay, you know that if you've got something that only needs to send this many transactions per second, then just don't give it enough token to do something weird. So it's a kind of...
We also have the notion of gas. If anybody is familiar with Ethereum-based systems, there is this notion of gas. And, within the public Ethereum system, gas is used as a mechanism for essentially to pay per compute. So you to interact with any contracts that exist in the public Ethereum network, you have to leverage gas. And the person sending the transaction, what they need to do is to use Ether to buy a sufficient number of gas that will operate the smart contract to the extent that they need it to be operated. In Burrow, we have kept the notion of gas, although we're a communistic system, in the sense that the gas price is, for the most part, permanently set at being zero. So you still need to send gas in order to do things, but that gas is free to you. It does not require any of the native token to do that, because the conversion price is zero. Now, why do we keep it? We keep it for a very simple reason, which is infinite loops within smart contracts. We need to have a mechanism that we can stop them somehow, or else the entire network would seize, because every validator would be thrown into an infinite loop. And by leveraging a maximum gas per transaction, which is a network level setting, then you can essentially stop loops, infinite loops that are going to be arbitrary or adverse to the forward progress of your network, but you still can live in a happy socialist or communist system where gas is free. So if anybody is familiar with gas, the notion of gas from Ethereum, that's how we deal with it in Burrow. So to be clear, this is the end of the prepared content. I'm really happy that we actually got this far. We weren't sure the audience in the room and how far we could get. We can stick around and answer questions. We can stick around and give you some ideas for where you could go now that you have this base. But I do want to say thank you for attending and bearing with us over the few bugs that we had along the way, particularly this really weird bug that you experienced.
The bugging features in the product are quite nice. What I can tell you.
Thanks.
Forensics.
Forensics is really nice, so I got more knowledge than I would expect.
Okay.
Usually you don't get that information on the first presentation. So
Yeah.
the rest I can try to do at home
Yeah.
from different slides.
Great.
Okay.
Yeah, so if anybody has questions, great. If not, I wish you a great evening.
But if you have a few more minutes, I'm definitely up for having a look at it. I've just been another command. Can you run that command?
Are they looking at it?
I'll come and join you down there.